Hello and welcome to this video out of my Networking Basics series. I'm Wolfgang Tremmel and I run the DE-CIX Academy. If you are interested in more video or other downloadable content like white papers, like recorded webinars or other interesting things, just have a look at our website, go to dcix.net/academy and have a look around. Today I'm going to talk about IP protocols, Ethernet, and how they are glued together. So let's head over to the presentation. This is part 6b out of my Networking Basics series, and the question is, why did I put it here? Well, the reason: to understand today's video and presentation, you need to know about IP protocols, you need to know about Ethernet, you also need to know what routing is and also what broadcast and multicast are. All these topics have been handled in previous videos. So if you're not sure or if you don't understand certain parts of this video, just go back, for example, to part 5, where I talk about Unicast, broadcast, multicast, and anycast. But today I'm going to talk about how IP and Ethernet work together. So what's the actual problem? If you remember how a router works, you remember that all IP packets do have a destination IP address. And when I talk about IP, I always mean both IPv4 and IPv6. Today, IPv4 and IPv6 will be handled separately, and I will mention which applies to which protocol. But this is for all IP protocols. All IP packets do have a destination IP address. And depending on that destination IP address of an IP packet, a router decides where to send it. He decides about the next hop. For this, he has a large table, and this is called, well, the routing table. The routing table doesn't contain millions of single entries. It contains IP prefixes. And I talk about all that when I talk about routing. So have a look at that video if you have missed it. So, but how does it work in detail? When a packet arrives at the router and he wants to send it to a next hop, how does it get there? Well, of course, to send it across an Ethernet, an IP packet has to be put into an Ethernet frame. Remember, when I talk about layer 2 protocols, I'm talking about frames. When I talk about IP on layer 3, I talk about packets. And this Ethernet frame also needs a destination Ethernet address, a so-called MAC address. So where to get this destination Ethernet address from? This is today's topic. The router only knows the IP address, but he needs to get the destination router's Ethernet address. So how to find an Ethernet address to a given IP address? Well, we need a method for that. For any given IP address on the LAN a router is connected to, or not even a router, a normal system like your laptop, also if it wants to communicate locally, it needs to know the Ethernet addresses of all the IP addresses in your local network. And in IPv4, the protocol to solve that is called ARP. That's the Address Resolution Protocol. In IPv6, this is called Neighbor Discovery. Both of them give you the Ethernet address for a given IP address, but they work quite differently. Let's talk about IPv4 first, because it's a little bit simpler. So how do I get an IPv4 address, an Ethernet address for a given IPv4 address? Let's just start on a local network with one host with an IP address. Of course, each of the sender also has to have an IP address, 192.0.2/18, and we have a /24 network. Of course, the sender knows its own Ethernet address. And what he doesn't know the Ethernet address of the receiver, of the target. He wants to send a packet to 192.0.2.33. He knows the IP address, but he doesn't know the target's Ethernet address. So that's what the sender needs to find out. And for that, we are using ARP Address Resolution Protocol. As the name says, it's a protocol. And ARP wasn't designed only for Ethernet, and it even wasn't designed only for IP. So it's kept pretty open. But in reality, I haven't seen it elsewhere, only with IPv4 and with Ethernet. But it's supposed to work with other protocols as well. How does it work? Well, in principle, we are using the broadcast ability of Ethernet. So we are broadcasting a request for an Ethernet address to all systems on the segment. We send our own Ethernet and our own IPv4 address, and we send the target's IPv4 address and just hope that somebody answers and sends us back the target's Ethernet address. That's what we are asking for. How does it look like? Well, this is an ARP request. That's the ARP packet. Like I said, it's not only designed for Ethernet, so the first thing we need to put in that we're actually dealing with a hardware type of Ethernet. We are dealing with a protocol of IPv4. We are using here the same value as the Ether type in an Ethernet frame. The hardware address, that's the length of the Ethernet address, it's 48 bits, so it's 6 octets, so we're putting in a 6 here. And the length of the protocol address, that's IPv4, that's 32 bits, 4 octets, so we're putting in a 4 here. And the operation 1 equals to, this is a request. Now the interesting stuff. We have to put in the request specific values. We put in the requestor Ethernet address, the requestor's IPv4 address, and we put in the target's IPv4 address. That's the address we need to know the Ethernet address for. We do not have the Ethernet address of the target, so we are leaving that blank. So this is now my ARP packet, and I'm putting that into an Ethernet frame. And since I do not know where to send it to, I'm simply broadcasting it to all systems on the segment. So I'm putting in as destination Ethernet address or destination MAC address, that's the same, putting in all ones, FF, and so on. That's the broadcast address. The source MAC address, well, that's my own. The Ether type is 806, and that's ARP. It has its own Ether type, and then I'm sending it on, and I'm broadcasting it to all systems. Well, broadcast. That's one of the main criticisms of ARP and one of the main problems we sometimes have. All ARP requests are sent via Ethernet broadcast. That means that every station on the LAN receives them and needs to process this. It's a broadcast, so it doesn't get stuck at the network adapter. It has to be passed on to the CPU and has to be checked. And now just imagine a large peering LAN like at DE-CIX Frankfurt with thousands of stations. There is a constant noise level of ARP broadcasts going on. And that for a large LAN like Frankfurt does make problems, because each of them needs to be processed by each and every station. Every station checks if the target IPv4 address equals its own, and that costs CPU cycles. Well, if not, the ARP request is discarded, of course, but if yes, the target sends an ARP reply. And the ARP reply, well, the packet looks quite the same. We have a 2 now in operation. That means a reply. Everything else in the header is the same. We are putting in the original target Ethernet address, and oops. Yeah, here we go. And this is what we actually look like. I messed up a little bit with the animation here, but not a problem. You see, this is the information now circled red, what the sender wants. The target address here in the packet is actually the requester's Ethernet address and IPv4 address. Remember, we're sending a packet back, so the values got swapped. And here in the sender Ethernet address, this is the value the requester needs to send IP traffic. And again, it goes into an Ethernet frame. Destination address is the requester. The source MAC address is the sender. And the ether type again is hexadecimal 806. So now you might ask, well, it's already in the Ethernet frame. Why does it have to go into the ARP part as well? Well, the reason for that is another system might answer in proxy for somebody else. This is called ARP proxy. It's bad, so I'm not talking a lot about it, but it is possible that the source MAC address and the requested address in the payload are different. The requester only looks at the payload to fill its ARP table. So in the payload is the requested information. Yeah, we talked about layers before, about the layers of the IP protocols, and the question now, on which layer is ARP? Well, it works directly on Ethernet, so it should be on layer 3. It is not restricted to IPv4, but it is not really on the internet layer. So let's put it here. Let's make the protocol stack for ARP like this. It's on layer 3, but it's not an IP packet, so it has its own protocol on layer 3. That's about ARP and how IPv4 routers get the Ethernet address for a given IPv4 address. Now let's talk about IPv6. The problem is quite the same. I'm going to send an IP packet, an IPv6 packet from my own host, and I want to know the Ethernet address for a given IPv6 address of a system where I want to send packets to. So what's the destination Ethernet address? How to find out? And if you remember, when I was talking about broadcast and multicast, there is no broadcast anymore in IPv6. It was discarded for good reasons, because simply in large LANs it makes too much noise. Instead, IPv6 stations, all IPv6 hosts, they join a number of multicast groups. So they tell their Ethernet adapter, I'm reachable on this multicast address and on this multicast address. Depending on the hardware, you can join a lot of multicast groups on an Ethernet basis. So you receive the packets for these multicast groups, but no longer for any broadcast. And but depending on the IPv6 address a station has, it joins the so-called solicited node multicast address. If you want to read more about it, there is an RFC. Just please download the PDFs of this presentation and have a look. There is a link you can click on. This multicast address in IPv6 writing it starts with FFO2 and it contains the last 6 bytes of the IPv6 address in question. So if I have a specific IPv6 address on my network adapter, I always join this multicast group where the last 6 bytes of my IPv6 address is in the multicast address. And this is mapped one-to-one also to an Ethernet multicast address. Remember, Ethernet has 48-byte address length, while IPv6 has 128-byte address length. So there needs to be a mapping, and there is a one-to-one mapping from IPv6 to Ethernet. So you don't really need broadcast. Multicast address to discover to a specific neighbor is possible. So how does the packet look like? We are using here a standard ICMPv6 packet, which is basically an IP packet, an IPv6 packet with ICMPv6 payload. So it's a standard packet. The source address is the requestor. The destination v6 address is the calculated multicast group. So it has at the end the last 6 digits are from the requested IPv6 address. The requested IPv6 address itself goes into the ICMPv6 part as a target v6 address, and also there is an option added to the ICMPv6 part which has the Ethernet address of the requestor in it. So this is how an IPv6 neighbor solicitation, neighbor discovery, request for an Ethernet frame, for an Ethernet address looks like. And if you look closely, it basically contains the same information like the ARP packet does, just in a different way. And again, it's put into the payload of an Ethernet frame. The main difference between v6 and v4 now is that we are not using broadcast, we are using multicast. This is the IPv6 multicast address we want to send to, and we are mapping that into an Ethernet multicast address. And if you have a look, it takes the last part of the IPv6 address and adds 3333 in front of that. So that's the Ethernet destination multicast address. Wow, it is complicated. Please stay with me. Please listen to it again, and also please have a look at the downloaded PDF. All information is also in there. The source MAC address, it's the sender's MAC address like before, and the ether type is standard IPv6. It's nothing special, it's a standard IPv6 packet. There is no need for a special Ethernet protocol here. So, the reply, it gets processed, gets sent back. The reply is also a standard IPv6 packet. The source address is hopefully the one we were asking for. We have an ICMPv6 payload. The source address, like I said, is the target. The destination address is the requestor. Then we are setting here some flags. There is a router flag, that means the request was sent by a router. There is a solicited flag, that means this is sent because somebody asked for it. and there is an override flag that means replace any entry you have with that one. The target IPv6 address, again, that's the requested address. That's what we asked for. And the Ethernet MAC address, that's what we really want, again, goes into an IPv6 option. And like I said, it's the same information like in IPv4 ARP, just a little bit more clever organized. No more broadcast and using a standard IPv6 packet, no need for a special protocol. Let's compare this. Let's compare IPv4 and IPv6. Communication. In IPv4 we are using broadcast, in IPv6 we are using multicast. So broadcast goes to all stations on the LAN, multicast only goes to a multicast group, and if you see how the multicast address is calculated, there is a good chance it only goes to one station. There might be two stations with the same end numbers, fine, but it's still not as bad as using broadcast. Stations involved. Well, like I said, in IPv4, that's all stations all the time. They get all the ARP requests as on broadcast. On multicast, it's a limited group, often just one, so we have a clear winner here with IPv6. The protocol which is used. In IPv4 we are using ARP, which is a protocol of its own. In IPv6 we are using ICMP version 6, which is part of IPv6. So again, in parts of standardization, also a clear winner here. And I would like in this contest declare IPv6 here is the winner in terms of cleverness of the design. And of course, when IPv6 was invented, was specified, they had years and years of experience of IPv4 and knew what they want to make better. So, conclusion, what did we talk about today? We talked about learning Ethernet addresses for IPv4 and IPv6. So to send traffic across an Ethernet to an IP node, a sender needs to learn that node's Ethernet address. IPv4 and IPv6 have different methods to solve this. IPv4 uses ARP, the address resolution protocol, on top of Ethernet. IPv4 broadcasts ARP requests and receives ARP replies. IPv6, on the other hand, uses ICMP version 6 for neighbor discovery, and IPv6 sends neighbor discovery requests to a multicast group it knows the receiver is in. So this is how getting Ethernet addresses to known IP addresses. Good. And with that, I say thank you for listening. It was a complex topic today, so have a look at Wikipedia, download the PDF, and if you're really interested, also read the RFC, the linked requests for comment, where all the details are specified. Thank you for listening. I'm Wolfgang Tremmel from the DE-CIX Academy. See you next time. Bye bye.